Imagine a moment, not so long ago in the grand scheme of things, when everything you see, touch, and even think about was crammed into a space smaller than a single atom. Sounds impossible, right? Yet, that's precisely where our story begins. We're about to embark on an epic journey, tracing the unbelievable adventure of existence itself, from that infinitesimally small beginning to the vast, star-dusted cosmos we explore today. Stick around, because understanding where we came from is the first step to truly appreciating where we're going. The Big Bang, a cosmic genesis. Imagine a time, before space, before anything we can comprehend. That's where our story of the universe begins, not with a bang in the way we typically think of an explosion, but with an incredibly rapid expansion. Think of it like blowing up a balloon, but instead of air, it was space itself that stretched out at an astonishing speed. In the very first fractions of a second, the universe went from being smaller than an atom to something immensely vast. It was a period of super-fast growth, like a toddler suddenly shooting up inches overnight, only on a cosmic scale. This initial burst of expansion is what we call inflation. As this cosmic balloon continued to inflate, things started to cool down. This cooling allowed the fundamental forces of nature, which were all jumbled together at the start, to separate. Gravity, electromagnetism, and the nuclear forces began to take on their distinct roles. It was like a chaotic orchestra where all the instruments were playing at once, and then, gradually, each section started to play its own part, creating a more ordered sound. In this early, hot soup of particles, matter and antimatter were being created and destroyed in equal measure. However, a tiny imbalance meant that for every billion particles of antimatter, there was 1,000,000,001 particles of matter. This slight surplus of matter is why we have a universe filled with stars, planets, and us. When matter and antimatter meet, they annihilate each other, turning into pure energy, like a tiny, spectacular firework. If it hadn't been for that minuscule leftover of matter, the universe would likely be a void of energy. Shortly after, as the universe cooled further, protons and neutrons started to form. These are the building blocks of atomic nuclei, like Lego bricks waiting to be assembled. Then came the formation of the first light elements, primarily hydrogen and helium. These were the simplest atoms, like the first letters of the cosmic alphabet. For hundreds of thousands of years, the universe was a dense, opaque fog of charged particles and light that couldn't travel freely. It was like trying to see through a thick cloud. Finally, when the universe cooled enough for electrons to bind with atomic nuclei, forming neutral atoms, light could finally travel unimpeded. This moment released the first light into the universe, a faint afterglow that we can still detect today as the cosmic microwave background radiation, a baby picture of the universe itself. Inflation, the universe's rapid expansion. Imagine the universe as a tiny, incredibly dense speck, smaller than the period at the end of this sentence. Then, in a blink of an eye, or rather, in an infinitesimally short period of time, it underwent a growth spurt like no other. This wasn't just a little stretch. It was an explosion of expansion, a cosmic unfurling that made the universe grow unimaginably large, faster than the speed of light. Think of it like blowing up a balloon, but instead of your breath, it was some mysterious energy, and instead of a few seconds, it happened in a fraction of a trillionth of a second. This period is called inflation. Before inflation, the universe was a bit of a mess. If you looked closely, you'd see that regions that were incredibly far apart seemed to have the same temperature. This is like finding two people on opposite sides of the planet who somehow have the exact same, very specific, pet peeve. How could they possibly have communicated that? Inflation solved this cosmic mystery by essentially squishing those distant regions together before the big stretch. It's as if the universe took a deep breath, expanded rapidly, and smoothed out all those little inconsistencies, making it remarkably uniform. This rapid expansion wasn't just about making things bigger, it was also about creating the seeds for everything we see today. Tiny quantum fluctuations, like little ripples on a pond, were stretched and magnified during inflation. These minuscule variations became the blueprints for galaxies, stars, and planets. Without inflation, the universe might have remained a uniform, boring soup, devoid of structure. It's like a baker carefully adding a pinch of this and a dash of that to a batter. Inflation was the cosmic chef's secret ingredient that made the universe interesting. The sheer speed and scale of inflation are mind-boggling. In a tiny fraction of a second, the universe went from being subatomic to being larger than a grapefruit. This rapid growth explains why the universe appears so flat and uniform on large scales. It's the cosmic equivalent of a tiny ant on a massive beach ball suddenly finding itself on a nearly flat surface as the ball inflates. This brief, powerful burst of expansion set the stage for all the subsequent cosmic evolution, a truly explosive start to our universe's grand story. The primordial soup, quarks and leptons. Imagine the universe right at the very beginning, not a single star or planet in sight. It was a chaotic, incredibly hot, and dense soup. Think of it like a supercharged, microscopic version of a thick, bubbling stew, but instead of carrots and potatoes, it was filled with the most fundamental building blocks of everything we know. These were the quarks and leptons, the tiny, tiny ingredients that would eventually cook up galaxies, stars, and even you. Quarks are like the Lego bricks of protons and neutrons, which in turn make up the core of atoms. There are 6 different flavors of quarks, though only 2 are stable enough to stick around in our everyday world, the up quark and the down quark. Protons are made of 2 up quarks and 1 down quark, while neutrons are made of 1 up quark and 2 down quarks. It's like a secret recipe where the number and type of quarks determine what kind of particle you get. These little guys were zipping around at lightning speed, constantly bumping into each other in that primordial inferno. Leptons, on the other hand, are a different bunch. The most famous lepton is the electron, the tiny particle that orbits the nucleus of an atom and is responsible for electricity. Other leptons include neutrinos, which are super elusive and barely interact with anything. Imagine trying to catch a ghost that's also a particle. Unlike quarks, leptons don't seem to combine to form larger particles. They exist as individuals, like tiny, independent marbles rolling around in that cosmic soup. This primordial soup was so hot that even these fundamental particles couldn't quite settle down. It was a wild, energetic dance where quarks and leptons were constantly being created and destroyed, a universe still figuring out its basic ingredients. It took a while for things to cool down enough for these quarks to finally pair up and form protons and neutrons, and for electrons to start orbiting them, laying the groundwork for the first atoms. Without this initial, incredibly energetic mix of quarks and leptons, none of the universe's subsequent wonders would have been possible. The first nuclei, forging light elements. Imagine the universe, not as it is today, but as a super hot, incredibly dense soup. This wasn't your grandma's chicken soup, though. This was a cosmic broth where things were happening at speeds we can barely comprehend. After the initial fiery bang, the universe cooled down just enough for something truly remarkable to occur. Protons and neutrons, the building blocks of atomic nuclei, started to get cozy. Think of it like a bunch of single Lego bricks suddenly deciding to snap together. This cosmic construction project, known as Big Bang nucleosynthesis, was all about forging the very first light elements. We're talking about hydrogen, the simplest atom with just 1 proton, and helium, which has 2 protons and usually 2 neutrons. A tiny sprinkle of lithium also made an appearance. It was a delicate dance of fusion, where these particles, energized by the still intense heat, bumped into each other and bonded. It's a bit like when you're trying to assemble a complicated piece of furniture, and suddenly, 2 pieces just click into place perfectly. The conditions were just right for a brief period. Too hot, and the newly formed nuclei would have been ripped apart. Too cool, and they wouldn't have had enough energy to fuse. It was a cosmic Goldilocks moment, a sweet spot that lasted only a few minutes. During this time, about 75% of the hydrogen and 25% of the helium in the entire universe were created. That's a massive amount of production in what, cosmically speaking, was the blink of an eye. These first forged elements, primarily hydrogen and helium, are the fundamental ingredients that would eventually form stars, galaxies, and everything we see today. It's mind-boggling to think that the stuff that makes up you and me, and the stars twinkling in the night sky, all began with this initial, brief period of element creation in the very young universe. Without this early forging of light elements, the universe as we know it simply wouldn't exist. It's the ultimate cosmic starter pack. The Cosmic Dark Ages, a universe unlit. The universe, after its explosive birth, entered a prolonged period of darkness. Imagine a brand new, enormous house that has just been built, but the electricians haven't finished wiring yet. The lights are all in place, but there's no power. This was the cosmic equivalent. For hundreds of millions of years, the universe was a vast, empty expanse, devoid of the stars and galaxies that would eventually illuminate it. It was a time before the first beacons of light ignited, a cosmic twilight where the only illumination came from the fading embers of the Big Bang itself. This was not a void of nothingness, however. It was filled with a diffuse soup of hydrogen and helium gas, the raw ingredients for everything that was to come. Think of it like a baker with all the ingredients for a magnificent cake: flour, sugar, eggs, but the oven hasn't been turned on. The potential for deliciousness is there, but it's not yet realized. In this early universe, gravity was slowly and patiently doing its work. It was like a gentle, invisible hand, coaxing the gas clouds to clump together. These clumps, initially small and diffuse, began to grow denser under their own weight. It's a bit like how dust bunnies under your bed, given enough time and a slight breeze, can coalesce into something more substantial. These nascent structures were the seeds of the first stars. Eventually, these gas clouds became so dense and so hot in their cores that a remarkable event occurred. Nuclear fusion ignited. This is the same process that powers our sun today. When the first stars flickered into existence, they were like massive celestial campfires, each one a blazing inferno in the otherwise dark cosmos. These were not the familiar, gentle stars we see tonight. They were colossal, burning incredibly hot and fast, living out their lives in a cosmic blink of an eye before exploding as supernovas. Their light, the first true starlight, began to push back against the darkness, marking the end of the universe's infancy. This reionization, as scientists call it, was the universe slowly getting its power turned back on, room by room. The first stars, igniting the cosmos. The universe, in its infancy, was a dark, uninteresting place. Imagine a vast, empty room, devoid of any light sources. For hundreds of millions of years, it was just that, a cosmic void filled with a thin soup of hydrogen and helium gas. This primordial gas, the leftover ingredients from the Big Bang, swirled and clumped together under the relentless pull of gravity. It was a slow, patient process, like watching dough rise, but on an unimaginably grand scale. These clumps grew larger and denser, their internal pressure building. Then, something magical happened. In the densest regions of these gas clouds, the pressure and temperature became so immense that the atoms of hydrogen began to fuse. This wasn't just a little sizzle. It was a nuclear inferno, a cosmic fireworks display that lit up the darkness. These were the very first stars, and they were giants. Unlike our sun, which is a relatively modest star, these early behemoths were hundreds, even thousands of times more massive. They burned incredibly hot and bright, blazing with a furious intensity that would dwarf any campfire you've ever seen. These first stars, often called population third stars, were pure and simple. They were made almost entirely of the hydrogen and helium that had been forged in the Big Bang, with very few of the heavier elements we find in stars today. Think of them as the universe's first, most basic building blocks. Their immense gravity meant they had short, dramatic lives. They burned through their fuel at an astonishing rate, living for only a few million years before collapsing under their own weight. When these colossal stars died, they didn't go out with a whimper. They went out with a bang, a supernova explosion of unimaginable power. These explosions were the universe's first cosmic kitchens, forging heavier elements like carbon, oxygen, and iron from the lighter ones. These elements were then scattered back into space, seeding the next generation of stars and planets. Without these fiery deaths, the universe would still be a barren place, lacking the ingredients for everything from planets to people. It's a bit like how a baker needs to mix flour, eggs, and sugar to create a cake. These first stars provided the essential cosmic ingredients for everything that came after. The first galaxies, cosmic neighborhoods form. Imagine the universe after the initial fiery birth. For a while, It was a bit like a toddler's playroom, with gas and dust scattered everywhere, but not much organized. Then, gravity, the universe's ultimate interior decorator, started to get busy. It began pulling these wisps of matter together, like a cosmic magnet. These weren't just random clumps. They were the very first seeds of something much grander. Think of it like dust bunnies under your couch, but instead of being a nuisance, these dust bunnies were destined to become cities. These early collections of gas and dust, drawn together by gravity, began to heat up and spin. Eventually, in the densest, hottest spots, the magic happened. Nuclear fusion ignited. This is the universe's way of saying, let there be light, and, more importantly, let there be stars. These first stars were massive, bright, and lived fast, dying young in spectacular supernova explosions. But their deaths were not in vain. They forged heavier elements, like the carbon in your coffee cup or the iron in your blood, and scattered them into space, enriching the cosmic soup for future generations of stars and galaxies. Over time, these stellar nurseries, these budding galaxies, started to bump into each other. Gravity, being the persistent force it is, continued to pull these growing systems together. What was once a lonely star or a small cluster of stars began to attract others, forming larger and larger structures. These were the first cosmic neighborhoods, where galaxies began to form groups and clusters. It was a bit like people moving into a new town. Initially, there are just a few houses, but soon, more people arrive, roads are built, and a community starts to form. These early galaxies weren't quite the majestic spirals or elliptical giants we see today. They were often smaller, more irregular, and a bit chaotic, like teenagers still figuring out their style. But within these nascent structures, the foundations for the universe's grand architecture were being laid. They were the pioneers, the first organized communities in the vast expanse, all thanks to the relentless, invisible hand of gravity and the explosive lives and deaths of the universe's first stars. The Milky Way's birth, our galactic home. Imagine a cosmic nursery, vast beyond comprehension, where the seeds of our very own galactic home were sown. It all began billions of years ago, not with a bang, but with a slow, gravitational dance of gas and dust. Think of it like a giant, invisible cloud, mostly hydrogen and helium, slowly being pulled together by its own weight. This wasn't a sudden event. It was a process that took eons, a patient accumulation of matter. Over time, these clumps grew larger and denser, like tiny dust bunnies under your bed, eventually forming a much bigger mess. As this primordial cloud collapsed, it began to spin. This spinning motion is crucial, much like how a figure skater pulls in their arms to spin faster. The faster it spun, the flatter it became, forming a disk. At the center of this spinning disk, the pressure and temperature became so intense that nuclear fusion ignited. This was the birth of the first stars, the initial sparks that would illuminate our nascent galaxy. These early stars were massive, much larger than our sun, and lived fast, dying spectacularly in supernova explosions that scattered heavier elements, the building blocks for future stars and planets, throughout the disk. These explosions were like cosmic recycling centers, enriching the surrounding gas and dust with elements like carbon, oxygen, and iron. Subsequent generations of stars formed from this enriched material, leading to a more diverse stellar population. Our Milky Way, in its early stages, was a much more chaotic place, a swirling vortex of gas, dust, and newborn stars. It was constantly being bombarded by smaller galaxies, which it would eventually absorb, adding to its mass and complexity. Think of it as a cosmic buffet where our galaxy was feasting on smaller galactic appetizers. Over billions of years, this process of accretion and star formation continued. The disk thickened, and a central bulge formed from older stars. Spiral arms began to emerge, vast structures where star formation is particularly active, like cosmic traffic jams of gas and young, bright stars. Our Sun, a second or third generation star, eventually formed in one of these spiral arms, about halfway out from the galactic center. The planets, including our Earth, then coalesced from the leftover disk of gas and dust orbiting our young Sunday. And so, our galactic home, the Milky Way, took its familiar shape, a grand spiral galaxy teeming with billions of stars, a testament to the universe's enduring power to create and evolve. The formation of the solar system, a stellar nursery. Our solar system wasn't always a serene collection of planets orbiting a solitary star. It began its life within a vast, swirling cloud of gas and dust, a cosmic maternity ward known as a nebula. Think of it like a giant, dusty cloud in space, far bigger than anything we can imagine. This nebula, primarily composed of hydrogen and helium, also contained heavier elements forged in the hearts of ancient, long-dead stars. These elements, like carbon, oxygen, and iron, were the building blocks of everything that would eventually form. Something triggered this quiescent cloud. Perhaps it was the shock wave from a nearby exploding star, a supernova. This cosmic nudge caused parts of the nebula to begin collapsing under their own gravity. As more and more material clumped together, the center of the collapsing cloud became incredibly dense and hot. It was like squeezing a giant snowball. The more snow you pack in, the denser and colder it gets in the middle. But in this case, it got incredibly hot. This spinning, superheated core was the birthplace of our sun. While the sun was forming at the center, the remaining gas and dust flattened into a spinning disk, much like a pizza dough being tossed. Within this protoplanetary disk, tiny particles began to stick together. These clumps grew larger, attracting more material through gravity. Imagine dust bunnies under your bed, but on a cosmic scale, growing and growing. These growing bodies, called planetesimals, were the ancestors of planets. Some grew big enough to become rocky planets like Earth and Mars, while others, in the colder outer regions of the disk, managed to gather vast amounts of gas, forming the gas giants like Jupiter and Saturn. It was a chaotic dance, with many collisions and near misses as these nascent worlds jockeyed for position. The Earth's genesis, a rocky beginning. Our planet wasn't always the vibrant blue marble we know. Imagine a chaotic cosmic nursery, a swirling mess of dust and gas left over from the birth of our sun. This primordial soup was the raw material from which Earth, along with its planetary siblings, began to take shape. Over millions of years, tiny particles of rock and metal, drawn together by gravity, started clumping up. It was a bit like dust bunnies forming under your bed, but on a cosmic scale and with a lot more heat. These growing clumps, called planetesimals, were essentially baby planets, constantly colliding and merging. The early Earth was a truly hellish place. It was a molten ball of rock and metal, hotter than the surface of the sun. There was no solid ground, no atmosphere as we understand it, just a seething inferno. Giant impacts were common. Think of a bowling ball hitting a water balloon, but with planets. One such colossal collision, believed to have involved a Mars-sized object named Theia, is thought to have ejected enough material to form our moon. This was a violent birth, to say the least, a cosmic demolition derby that shaped our world for eons. As this fiery chaos slowly subsided, the Earth began to cool. A crust started to form, like a scab on a giant wound. But this new skin was unstable, constantly being broken apart and reformed by the intense heat bubbling up from the planet's interior. Volcanoes erupted everywhere, spewing out gases that would eventually form our atmosphere. Water, likely delivered by comets and asteroids, began to accumulate, forming the first oceans. This was a slow, gradual process, taking hundreds of millions of years, turning a molten mess into a dynamic, albeit still very active, planet. It was the very beginning of a long journey, from a barren rock to the cradle of life. The moon's creation, a giant impact. Imagine the early solar system, a cosmic demolition derby where planets were still being formed. Our young Earth, still molten and gooey, was minding its own business when Bam, a Mars-sized protoplanet, let's call it Theia, slammed into it. This wasn't a fender bender, it was a catastrophic collision, like dropping a watermelon on a jelly donut. The impact was so immense that it vaporized chunks of both Earth and Theia, sending a massive cloud of molten rock and debris hurtling into space. This fiery debris didn't just drift away into the cosmic void. Instead, it began to orbit our wounded planet, like a swarm of angry fireflies. Over time, gravity, that invisible cosmic glue, started pulling these bits and pieces together. Think of it like dust bunnies forming under your bed, but on a much grander and much hotter scale. Slowly but surely, this swirling collection of molten goo coalesced, spinning and merging until, after a few thousand years, which is practically overnight in cosmic terms, our moon was born. This giant impact theory explains a lot about the moon. For instance, it accounts for why the moon is made of similar stuff to Earth's outer layers, the mantle. It's like a cosmic divorce settlement, where the moon got a big chunk of Earth's rocky exterior. It also helps explain why the moon has a much smaller iron core than Earth, as most of Thea's core likely merged with Earth's. So, the next time you look up at the moon, remember it's not just a pretty face. It's a testament to a violent, yet ultimately creative, cosmic event. The dawn of life, a biological spark. The spark of life, a truly mind-boggling event, began not with a bang, but perhaps with a gentle nudge from chemistry. Picture the early Earth, a chaotic place with bubbling oceans and a sky that might have looked a bit alien. In this primordial soup, simple inorganic molecules, like building blocks from a cosmic Lego set, started to bump into each other. Through a series of fortunate chemical reactions, perhaps fueled by lightning strikes or volcanic heat, these humble components began to link up, forming more complex chains. Think of it like a bunch of single amino acids, the tiny bits that make up proteins, deciding to hold hands and form a little party. These early chains were the precursors to what we now call organic molecules, the very stuff of life. They weren't alive yet, mind you, but they were getting closer. Over vast stretches of time, these chains grew longer and more intricate. Some began to develop the ability to store information, like a primitive kind of biological hard drive, and others started to act as tiny factories, carrying out specific chemical tasks. It's a bit like having a set of tools scattered around, and then suddenly, they start organizing themselves into a toolbox. Then came the big leap, self-replication. This is where things get really interesting. Imagine a molecule that could make a copy of itself. It's like finding a recipe that, once you follow it, magically produces another identical recipe. This ability to reproduce, to pass on its own blueprint, is a hallmark of life. These early replicators, perhaps simple RNA molecules, were the first true biological entities. They were like the original, slightly clumsy, photocopiers of the universe, making imperfect but functional duplicates. These self-replicating molecules eventually got enclosed within protective membranes, forming the first simple cells. These membranes acted like tiny bubbles, keeping the precious internal machinery safe from the harsh external environment. It was a bit like putting your most valuable possessions inside a sturdy box. These early cells were incredibly basic, single-celled organisms, likely living a quiet life at the bottom of the ocean, probably not worrying too much about their next meal or the latest cosmic gossip. But from these humble beginnings, life began its incredible journey of diversification and evolution, a journey that continues to this very day. The Cambrian explosion, a burst of diversity. Suddenly, life on Earth decided to throw a massive party, and it was called the Cambrian explosion. For billions of years, life had been pretty simple, mostly tiny, squishy things floating around. Think of it like a world populated only by single-celled organisms and maybe some very, very basic blobs. Then BM. Over a relatively short period, maybe around 20 million years, the planet went from a minimalist art show to a full-blown biodiversity carnival. Imagine a quiet town suddenly getting a population boom of eccentric inventors, flamboyant artists, and busy entrepreneurs, all arriving at once. That's what happened to the oceans. Creatures with hard shells, like the first trilobites, scuttled across the seabed. These guys were like the ancient cockroaches of the ocean, tough and surprisingly successful. We also saw the emergence of predators, with weird, grasping appendages, ready to try out the new buffet. It was a real arms race, but with more goo and fewer machine guns. This explosion wasn't just about adding more types of creatures. It was about inventing entirely new ways of being alive. We saw the development of complex body plans, with heads, tails, and specialized organs. Animals started to have guts, which is a big deal if you think about it. Suddenly, you could actually digest your food instead of just absorbing it through your skin. This period gave us the basic blueprints for most of the animal groups we see today, from worms to our own distant ancestors. It was the ultimate evolutionary try it and see what sticks experiment, and thankfully for us, some of it really did stick. The age of dinosaurs, giants roamed the Earth. For an astonishing stretch of time, Earth belonged to colossal creatures that dwarfed anything we see today. These were the dinosaurs, rulers of a world vastly different from our own. Picture a landscape where ferns grew as tall as trees and the air was thick with the buzzing of giant insects. It was a realm perfectly suited for these magnificent beasts. Think of Tyrannosaurus rex, the undisputed king of predators, with jaws powerful enough to crush bone. Or the gentle giants like Brachiosaurus, whose necks stretched towards the heavens, reaching leaves on the highest branches, much like a giraffe might stretch for a tasty acacia leaf, but on an epic scale. These ancient reptiles weren't just big, they were incredibly diverse. From the armored Ankylosaurus, a walking tank with a club tail capable of delivering a knockout blow, to the speedy velociraptors, pack hunters that likely worked together to bring down prey, there was a dinosaur for every ecological niche. Some, like Stegosaurus, sported bony plates along their backs, perhaps for display or to help regulate their body temperature, a bit like a lizard basking in the sun to warm up. Others, like Triceratops, boasted impressive horns and frills, formidable defenses against the fiercest predators. It was a world of constant struggle and adaptation, where survival of the fittest was the ultimate law. The sheer scale of these animals is mind-boggling. Imagine a herd of Diplodocus, stretching for hundreds of feet, moving across the land like a living, breathing train. Their long tails would have acted as counterbalances, helping them to maneuver their immense bodies. The eggs they laid were also enormous, some as big as footballs, needing careful incubation to bring forth the next generation. Life for these giants was a constant search for food, with herbivores needing to consume vast quantities of plant matter daily to sustain themselves. Predators, on the other hand, were always on the hunt, their senses honed to detect the slightest movement or scent. Then, as suddenly as they appeared, they vanished. A catastrophic event, likely a massive asteroid impact, plunged the world into darkness and chaos, wiping out the dinosaurs and paving the way for new life forms to emerge. The legacy of these giants, however, lives on in the fossil record, offering us a breathtaking glimpse into a lost world, a time when Earth truly was the land of giants. The KPG extinction, a cosmic catastrophe. The Earth remembers a truly spectacular, albeit terrifying, event that reshaped life as we know it, the KPG extinction. Imagine a cosmic bowling ball, but instead of a sphere, it was an asteroid roughly 6 miles wide, hurtling through space at speeds that would make a fighter jet look like a snail. This wasn't just any rock. It was a planet killer, destined for a fiery embrace with our very own world. This colossal impactor slammed into what is now the Yucatan Peninsula in Mexico, unleashing energy equivalent to billions of atomic bombs. The initial blast vaporized rock, creating a crater over 100 miles across. But the devastation didn't stop there. The impact sent shockwaves rippling through the planet, triggering massive earthquakes and volcanic eruptions on a scale we can barely comprehend. Think of dropping a pebble into a pond, but instead of ripples, you get tsunamis hundreds of feet high, sweeping across continents. The immediate aftermath was apocalyptic. The sky, choked with dust and debris thrown miles high, plunged the planet into a prolonged, sun-blocking darkness. This impact winter caused temperatures to plummet, effectively shutting down photosynthesis, the process plants use to make food. Without sunlight, plants died, and with plants gone, the herbivores starved, followed swiftly by the carnivores. It was a domino effect of doom, a catastrophic unraveling of the food web. Yet, amidst this global tragedy, life found a way to persist. Small, resilient creatures, like mammals and birds, managed to survive in burrows or by scavenging. These survivors, like the unassuming mice of today, became the ancestors of the diverse life forms that would eventually repopulate the Earth. This cosmic catastrophe, while devastating, cleared the stage for a new act, paving the way for the rise of mammals, including, eventually, us. It's a stark reminder that even the most profound changes can emerge from the most destructive events. The rise of mammals, survivors, and successors. The world shifted dramatically after the colossal asteroid impact, a cosmic oopsie that wiped out the dinosaurs. Suddenly, the dominant lizards were gone, leaving a rather large, dinosaur-shaped hole in the ecosystem. This was the golden ticket for mammals, tiny, furry creatures who had been living in the shadows, mostly as nocturnal snack dodgers. Think of them as the ultimate survivors, the ones who patiently waited for their chance to shine. These early mammals were a far cry from the majestic lions or intelligent dolphins we know today. They were small, often no bigger than a shrew, and scurried around on four legs, munching on insects and whatever else they could find. But they possessed a secret weapon: warm blood. Unlike their cold-blooded dino overlords, mammals could keep their internal temperature steady, allowing them to be active in cooler temperatures and at night, when the dinosaurs were mostly snoozing. Plus, they nursed their young with milk, a pretty neat trick that gave their offspring a head start in life. As the dust settled and the planet began to heal, mammals started to diversify. With no T-Rex breathing down their necks, they began to explore new niches. Some stayed small and rodent-like, becoming masters of the undergrowth. Others grew larger, evolving into herbivores, then carnivores, filling the predator roles left vacant by the dinosaurs. It was a massive evolutionary party, and everyone was invited, as long as they had fur and could produce milk. This period saw the rise of incredible diversity. Imagine a world where creatures resembling primitive horses, early bears, and even the ancestors of bats began to appear. The oceans started to fill with whale-like mammals, and the skies, once ruled by pterosaurs, saw the emergence of flying mammals. It was a grand experiment in adaptation, with life taking countless new forms, all thanks to that one very unfortunate asteroid and the resilience of a small, furry group of survivors. The evolution of humans, our ancestral journey. Our story begins not with us, but with creatures that looked nothing like us. Think of them as our very, very distant cousins, some living millions of years ago. These early ancestors were more ape-like, walking on all fours for the most part, but a crucial change was brewing. They started to stand up, even if just a little. This might seem small, but imagine trying to pick berries or spot a predator. Having your hands free and a better view makes a huge difference. It's like when you're trying to find your keys in a messy room. Standing up gives you a better perspective. This upright posture, called bipedalism, was a game changer. It freed up their hands for all sorts of new tasks. Instead of just holding on, they could now carry things, food, tools, even babies. This allowed for more complex social interactions and the sharing of resources. Think of it as upgrading from a flip phone to a smartphone. Suddenly, you can do so much more. Over time, these early hominins, as scientists call them, developed slightly larger brains. This wasn't an overnight transformation. It was a slow, gradual process, like watching a plant grow, millimeter by millimeter. As brains grew, so did our ancestors' abilities. They became more adept at using tools. At first, these were simple stones, perhaps chipped to make a sharper edge for cutting or scraping. Later, they learned to control fire. Fire was revolutionary. It provided warmth, protection from predators, and a way to cook food, making it easier to digest and unlocking more nutrients. Imagine going from eating raw veggies all the time to having a delicious, roasted meal, a definite upgrade in comfort and energy. These developing skills, coupled with environmental changes that often push them to adapt, led to the emergence of various human species. Some of these species eventually died out, like branches falling off a tree, but one lineage persevered. This lineage eventually led to us, Homo sapiens. We are the product of millions of years of trial and error, of adapting, innovating, and surviving. Our journey from those early, ape-like ancestors to the complex beings we are today is a testament to resilience and the incredible power of evolution. The Ice Ages, a shifting climate. The Earth's climate has never been a steady affair. For eons, it's been on a wild roller coaster, with periods of intense cold, known as ice ages, playing a starring role. These aren't just a few chilly weeks. We're talking about vast expanses of time, spanning millions of years, when enormous ice sheets, thicker than skyscrapers, have covered huge swathes of our planet. Think of it like your freezer going into overdrive, but on a global scale, and for longer than you've been alive, or your grandparents, or even their grandparents. These icy behemoths crept down from the poles, grinding mountains into dust and carving out valleys that we still see today. These dramatic shifts weren't caused by a single event, but rather a complex dance of factors. Changes in Earth's orbit, subtle wobbles that alter how much sunlight we receive, are like the dimmer switch for our planet's temperature. When these orbital cycles align just right, they can nudge the climate towards cooling. Volcanic eruptions, spewing massive amounts of ash and gas into the atmosphere, can also act like a giant sunshade, temporarily blocking sunlight and triggering colder spells. And then there's the internal feedback loop of ice itself. Once a little bit of ice forms, it reflects more sunlight back into space, making things even colder, which leads to more ice. It's a bit like a snowball effect, but with potentially disastrous consequences for life. When the ice sheets advanced, they dramatically reshaped the landscape. Imagine giant bulldozers, but made of ice, slowly but surely pushing everything in their path. Coastlines were redrawn. Sea levels dropped significantly as water got locked up in the ice, and vast areas of land that are now underwater were exposed. This created land bridges, allowing animals and even early humans to migrate across continents. For instance, the land bridge that once connected Siberia and Alaska, now submerged beneath the Bering Strait, was a highway for ancient life. On the flip side, when the ice receded, the land rebounded, and new lakes and rivers were formed. It was a constant process of sculpting and reshaping, a geological art project on a grand scale, all driven by shifting temperatures. Life, of course, had to adapt or perish. During glacial periods, many species retreated to warmer refuges, much like we seek shelter indoors when it's freezing outside. Others evolved thicker fur or different behaviors to survive the harsh conditions. Think of the woolly mammoths, with their shaggy coats and thick layer of fat, perfectly suited for the icy tundra. When the climate warmed and the ice retreated, new ecosystems emerged, and species that had survived the cold began to spread into newly available habitats. This cycle of advance and retreat, of cooling and warming, has been a powerful engine of evolution, constantly testing the resilience of life on Earth and shaping the biodiversity we see today. The agricultural revolution, settling down. The world was changing. For millennia, humans had been nomads, following herds of animals and gathering wild plants. It was a life of constant movement, a perpetual scavenger hunt. Then, something shifted. People began to notice that if they dropped a seed, a new plant would grow. This wasn't exactly rocket science, but it was a game changer. Instead of just picking berries, they started planting them. Instead of just chasing bison, they began to domesticate animals. It was like deciding to host a potluck instead of constantly going out for fast food. This shift, known as the agricultural revolution, meant people could stay in one place. Imagine the relief. No more packing up your cave dwelling every few months. They built permanent homes, villages, and eventually towns. This stability allowed for new things to develop. With more reliable food sources, populations grew. More people meant more ideas, more hands to build, and more mouths to feed, which in turn spurred further agricultural innovation. It was a virtuous cycle, albeit one that sometimes involved a lot of manure. Farming was hard work, mind you. It required understanding seasons, soil, and the fickle nature of weather. But the rewards were immense. Surplus food meant not everyone had to be a farmer. Some people could become artisans, making tools and pottery. Others could become leaders or priests. This specialization led to more complex societies. Suddenly, you had people who were really good at making pots, and others who were really good at, well, organizing things and telling everyone else what to do. It was the dawn of a more organized, and sometimes more complicated, way of life. The rise of civilizations, building societies. Humans, once nomadic wanderers, began to settle down. They discovered that staying in one place, especially near fertile land and water sources, allowed them to grow their own food. This agricultural revolution was a game changer. Instead of constantly searching for berries and hunting game, people could cultivate crops like wheat and barley and domesticate animals such as sheep and cattle. This meant a more stable food supply, which in turn allowed populations to grow. Think of it like switching from a diet of random snacks to a well-planned meal prep. Suddenly, there was less scurrying and more, well, sitting around planning things. With more food came more people, and more people meant the need for organization. Small villages slowly grew into larger settlements. People started specializing in tasks beyond farming. Some became builders, constructing more permanent homes and public structures. Others became artisans, crafting tools, pottery, and jewelry. There were even early administrators who, we can only assume, spent their days trying to figure out who owed whom how many bushels of grain. This division of labor was crucial. It meant tasks could be done more efficiently and new skills could develop. It's like a modern office, but with way less PowerPoint and a lot more mud bricks. These growing settlements needed rules and a way to manage resources. This is where the earliest forms of government and social structures emerged. Leaders, often those who were strongest, wisest, or perhaps just loudest, began to organize defense, manage trade, and resolve disputes. Laws, whether written down or passed through oral tradition, helped maintain order. Early cities, like those in Mesopotamia or the Indus Valley, became centers of trade, culture, and innovation. People developed writing systems to keep records, invented currency to facilitate exchange, and built impressive monuments that still stand as testaments to their ingenuity. It was a messy, fascinating process, like toddlers learning to share toys, but on a much grander, civilization-building scale. The development of these societies wasn't always a smooth path. Competition for resources could lead to conflict, and not everyone benefited equally from these new arrangements. Yet, the fundamental shift from scattered bands to organized communities laid the groundwork for everything that followed. It was the moment humanity collectively decided to stop just surviving and start living in a structured way, complete with neighbors to borrow sugar from and occasional arguments over property lines. This period marked the true birth of complex human societies, a testament to our ability to cooperate, innovate, and, occasionally, argue over who gets the best spot by the river. The scientific revolution, unlocking nature's secrets. For centuries, humanity's understanding of the cosmos and the workings of the physical world was largely based on ancient texts and philosophical speculation. Think of it like trying to fix a car with only a dusty old manual from the 1700s, mostly guesswork and hoping for the best. Then, something shifted. A wave of thinkers began to question the established order, not with angry protests, but with keen observation and meticulous experimentation. They started to believe that nature had its own set of rules, a kind of cosmic instruction manual, and that through careful study, we could actually read it. This new approach, often called the scientific revolution, was like swapping that ancient manual for a modern toolkit. Instead of just accepting what Aristotle said about how things fall, people like Galileo Galilei started dropping things from towers, though maybe not that high, for safety reasons, and timing them. They built instruments, like telescopes that allowed them to see the moon not as a smooth, ethereal orb, but as a rocky, cratered world, much like our own. This wasn't about magic or divine pronouncements. It was about looking, measuring, and repeating. It was a fundamental change in how we sought knowledge, moving from pronouncements to proof. One of the biggest breakthroughs came with understanding motion and gravity. Before, people might have thought that things stopped moving when you stopped pushing them because they simply wanted to be still. Isaac Newton, however, proposed that an invisible force, gravity, was at play, constantly pulling things towards each other. This same force that makes an apple fall from a tree is what keeps the moon in orbit around the Earth, and the Earth in orbit around the sun. It's a universal law, like a cosmic dance choreographer, dictating the movements of everything from tiny particles to giant stars. This idea was so powerful because it explained so much with such elegant simplicity, proving that the universe wasn't chaotic but governed by predictable, discoverable principles. The impact of this revolution rippled through every aspect of life. Suddenly, the universe seemed less like a mysterious, unpredictable stage and more like a vast, intricate machine that could be understood and even harnessed. This shift in thinking paved the way for everything from improved navigation at sea, allowing for bolder explorations, to the eventual development of technologies that would transform society. It was the dawn of a new era, where curiosity, observation, and a healthy dose of skepticism became the most powerful tools humanity possessed in its quest to unravel the universe's deepest secrets. The space age, reaching for the stars. Humanity's leap beyond Earth's embrace began not with a gentle nudge, but a fiery roar. For millennia, the stars were mere pinpricks of light, objects of myth and distant wonder. Then, in a blink of cosmic history, we started to touch them. This new era, the space age, dawned as nations, driven by a potent mix of scientific curiosity and geopolitical rivalry, poured resources into conquering the void. Think of it like a global competition, but instead of a trophy, the prize was a place among the celestial bodies. The initial steps were tentative, like a baby bird testing its wings. Satellites, essentially robotic eyes and ears, were the first to venture out. These marvels of engineering, launched with immense power, orbited our planet, sending back invaluable data. They revolutionized communication, allowing us to connect across vast distances almost instantaneously, and provided us with weather forecasts that, while sometimes comically inaccurate, are still incredibly useful. Imagine trying to plan a picnic without knowing if it's going to rain. These satellites helped make that a distant memory. Then came the ultimate dare, sending living beings into the inky blackness. The first humans to venture beyond Earth's atmosphere were pioneers in the truest sense, strapping themselves into rockets that looked more like metal cans than comfortable cabins. These brave souls orbited our planet, experiencing weightlessness, a sensation akin to being perpetually on a roller coaster without the stomach-churning drops. Their journeys, though brief by today's standards, were monumental achievements, proving that the human body could, indeed, survive and function in space. It was a testament to our ingenuity, a bold declaration that Earth was no longer our only home. This era wasn't just about putting flags on the moon, though that was certainly a spectacular highlight. It was about building a persistent presence beyond our atmosphere. Space stations, like orbiting hotels for astronauts, became the next frontier. These complex structures allowed for longer stays, enabling scientists to conduct experiments that are impossible to perform under Earth's gravity. From studying how plants grow in space to understanding the effects of prolonged weightlessness on the human body, these stations have yielded a treasure trove of knowledge, pushing the boundaries of what we know about both the universe and ourselves. The search for exoplanets, other worlds abound. For centuries, people have gazed at the night sky and wondered if there were other worlds out there, other suns with their own planets. It's a question as old as humanity itself, like wondering if there's pizza on Mars. Spoiler, probably not, but a planet with pizza would be cool. It wasn't until relatively recently, though, that we had the tools to actually start looking for these distant worlds. Think of it like trying to find a specific tiny pebble on a beach from a mile away. You need a really good magnifying glass, or in our case, incredibly sensitive telescopes. These distant planets, called exoplanets, are tricky to spot. They're like tiny fireflies flitting around a giant spotlight, and the spotlight, the star, is so bright it usually washes them out. So, astronomers developed clever ways to see them indirectly. One popular method is the transit method. Imagine a moth flying in front of a distant street lamp. As the moth passes, it blocks a tiny bit of the light, causing a slight, temporary dimming. Astronomers do the same thing. They watch stars for these minuscule dips in brightness, which can signal that a planet is passing in front of its star from our point of view. It's like cosmic hide-and-seek, but with light. Another ingenious technique is the radial velocity method, sometimes called the wobble method. Even though a star is vastly more massive than its orbiting planets, the planets still exert a gravitational pull. This pull makes the star wobble slightly, like a dancer being pulled by their partner. By measuring these tiny shifts in the star's light, astronomers can detect the gravitational tug of an unseen planet. It's a bit like hearing the faint rumble of a truck going by even when you can't see it, just by feeling the vibrations. These methods have been incredibly successful. Thanks to these and other techniques, we've discovered thousands of exoplanets. They come in all sorts of flavors: giant gas planets bigger than Jupiter, rocky worlds similar to Earth, and even some that are just plain weird, like planets made mostly of diamond. Some orbit their stars so closely they have scorching hot surfaces, while others are so far out they're frozen wastelands. The sheer diversity is astonishing, and it tells us that our own solar system, with its familiar planets, might just be one of countless variations on a cosmic theme. We're no longer just guessing. We're cataloging entire neighborhoods of stars, each potentially with its own unique collection of worlds. The mysteries of dark matter and dark energy, the unseen universe. Imagine the universe as a grand cosmic party. We see the guests, the stars, planets, galaxies, all dancing and interacting. But what if most of the attendees are invisible, yet their presence profoundly influences the whole event? That's the mind-bending reality of dark matter and dark energy. Scientists estimate that all the stuff we can see, from the tiniest atom to the largest galaxy cluster, makes up only about 5% of the universe's total mass energy content. The rest, a staggering 95% is made up of these mysterious, unseen components. Dark matter is like an invisible glue holding galaxies together. Without it, galaxies would spin themselves apart, like a merry-go-round with too many riders flying off. Astronomers noticed that galaxies rotate much faster than they should based on the visible matter alone. It's as if there's extra gravitational pull from something we can't detect with telescopes. This invisible stuff doesn't emit, absorb, or reflect light, making it incredibly difficult to find. Think of it like trying to find a ghost at a party. You can see its effects, the doors opening and closing, the furniture moving, but you can't see the ghost itself. This unseen mass warps the fabric of space-time, bending light from distant objects as it passes by, a phenomenon called gravitational lensing. It's the universe's way of showing us that something is there, even if we can't lay eyes on it. Then there's dark energy, an even more enigmatic force. While dark matter acts as a gravitational anchor, dark energy seems to be pushing the universe apart. For a long time, scientists assumed that the expansion of the universe, set in motion by the Big Bang, would be slowing down due to gravity. However, observations of distant supernovae in the late 1990s revealed the opposite. The expansion is actually accelerating. This acceleration implies the existence of a repulsive force, a sort of cosmic anti-gravity, that permeates all of space. It's like discovering that the party isn't just continuing, it's actively getting bigger, with the walls of the room itself stretching outwards at an ever-increasing rate. The nature of both dark matter and dark energy remains one of the biggest puzzles in modern physics. Are they exotic particles, modified laws of gravity, or something entirely beyond our current understanding? Scientists are employing a variety of ingenious experiments, from underground detectors looking for dark matter particles to vast sky surveys mapping the distribution of galaxies, all in an effort to shed light on these invisible cosmic architects. The quest to understand dark matter and dark energy is not just about solving an astronomical riddle. It's about understanding the fundamental constituents and destiny of our entire universe. It's a cosmic treasure hunt where the treasure is the very fabric of reality. The future of the universe, what lies ahead? The cosmos is on a grand, albeit slow, journey. For billions of years, the universe has been expanding, and current observations strongly suggest this expansion isn't just continuing, it's actually speeding up. Think of it like a loaf of raisin bread baking in an oven. As the dough rises, all the raisins, galaxies, move further apart from each other. But in our universe's case, the dough itself is getting stretchier, making the raisins reseed even faster over time. This accelerated expansion is attributed to something scientists have dubbed dark energy, a mysterious force that seems to permeate all of space. We don't know exactly what dark energy is, but its effects are undeniable, pushing galaxies apart with increasing vigor. So, what does this mean for the ultimate fate of everything? The most widely accepted scenario is called the Big Freeze, or sometimes the heat death. As the universe continues to expand and cool, stars will eventually burn out, one by one, like candles in a vast, dark room. Galaxies will drift so far apart that they'll become isolated islands in an ever-emptier void. Even black holes, the universe's ultimate cosmic vacuum cleaners, aren't immortal. They are predicted to slowly evaporate over unfathomably long timescales through a process called Hawking radiation. like a leaky faucet dripping away the universe's energy. Eventually, the universe will reach a state of maximum entropy, meaning everything will be spread out so thinly and evenly that no further work or complex processes can occur. It will be a cold, dark, and incredibly dilute place, devoid of any structure or activity. Imagine a perfectly still, perfectly cold ocean stretching out forever, with not a single ripple or wave. This isn't a tomorrow problem, mind you. We're talking about timescales so vast they make the age of the universe seem like a blink of an eye. It's a rather bleak prospect, but it's the logical conclusion based on our current understanding of physics. However, the universe is full of surprises, and our understanding is constantly evolving. While the Big Freeze is the leading contender, other, more dramatic possibilities exist, though they are less favored by current evidence. One such idea is the Big Rip, where dark energy's influence becomes so strong that it not only pushes galaxies apart, but eventually tears apart stars, planets, and even atoms themselves. Another thought, though largely theoretical, is a cyclical universe, where a collapse and subsequent rebirth might occur, though the mechanisms for this are highly speculative. For now, though, the silent, cold expansion towards a state of ultimate stillness appears to be the most likely ending to our cosmic story. And so, from the smallest spark to the grandest galaxy, we've journeyed through billions of years. We've seen stars ignite, planets form, and life, against all odds, take root. It's a story of immense scale, a cosmic ballet of creation and destruction, all playing out in the silent theater of space. Think about it. You, right here, right now, are a product of this incredible, ongoing saga. Pretty wild, huh? If this mind-bending trip through time has left you curious for more, hit that subscribe button and ring the notification bell. You won't want to miss our next dive into the cosmos, where we'll be exploring the mind-boggling mysteries of black holes, those cosmic vacuum cleaners that even light can't escape.